Homework 3.5, Rational Functions, Video 1. This is the first video in the series of videos for the last homework that will be on Test 3. Just a reminder, this homework and Test 3 will be due on Wednesday, May 27th, 2020 at 11:59 p.m. Now you may be wondering why there's nothing on the board. Because in this series of videos, I decided to show you a lot of graphing things on Desmos.com. But I'll start every video pointing at the board so that we can have the section, the video number, and all that other stuff. But in these videos, like this one, I'll just take my camera and move it down here. Give me a second to walk around on the other side of the setup. In case you're wondering, I have one table stacked on top of another so that I can get the camera high enough when I'm at the board. And let's get this set up so that you can see this computer screen. Now this tripod acts really persnickety, so hopefully it'll cooperate. I'll just do this. I'll just have to hold it in the hand and use one hand on the computer. Okay, so in this homework and in this series of videos, we're going to be looking at functions that are rational functions. And what I mean by rational functions, this function f of x, is a ratio of polynomials. We've seen rational functions before. When we did the section back on test 2 about finding domains of functions, one type of function was a rational function. But in this series of videos, we're going to focus on graphing rational functions and how we can predict in advance features of the graph of a rational function before we actually go to graph it. Now, for now, let's not worry about this particular function, and I'm going to close this folder so that we can just look at a generic point on the graph. And I've got a slider set up so that there's a point on the graph. You can kind of see it in the screen right now. It's right here. And if I move this slider left or right, or even drag this point left or right, I think I can do that here, click and drag, yep. So I can either move the point on the graph or I can, oops, didn't mean to zoom in. Go back to home for a second. Or I can go click over here and then drag the slider left and right. Another thing that you can do is animate it by clicking this arrow, and it will automatically move the point around. And what it's doing, oh, where'd it go? Oh, there it is. What it's doing is it's moving the value of k, and so it's plotting an ordered point by putting in the x and then putting the x value into the function to create the y value. And where did the point go? There it is, it's over there. It's gonna come back. Actually, it's not. It's going all the way to 20. I would have to zoom out some. There it is. See, it's just chugging along. Well, that's interesting. The x is getting bigger, but the y is fairly static. Let me pause it. In fact, this portion of the graph almost looks horizontal. While that point's sitting over here, let's take a look at this graph and see if we can notice things about it that we haven't seen in the graphs of polynomial functions. You'll notice I've got some dashed lines. Those lines aren't technically part of the graph, and I'll turn them off just for a second. The graph of the function is there. The graph of this function is right here. But you'll notice this graph seems to be broken into pieces. There's a piece over here, there's a piece over here, and there's a piece up there. And if you're wondering, are they connected? The short answer is no, but if I keep zooming out, you'll see that this piece in the middle just shoots up, almost like a parabola, except it's not going forever left and right. And these two little boomerang pieces over here seem like they're dropping straight down, and it looks like they're almost vertical. They're not, but it almost looks that way. Let me go back to the home screen. If I can find my arrow, there it is. So anyway, let's zoom out one. So what we're going to try to do in analyzing these rational functions is figure out where are these lines. And let me turn them back on. By the way, those lines are just horizontal and vertical lines, which is why their equations are so simple. X equals -2 is this vertical line over there. Excuse me, x equals +2. X equals -3 is that vertical line. I'm just turning the graph on and off. And then y equals -1 is this horizontal line. So one thing we're going to try to figure out is where do these lines come from in the function? And looking up here, you might be able to figure it out just by looking, but we'll get into the details in a moment. But I also want to describe what these lines are doing, because these lines aren't actually part of the graph. These lines are called asymptotes. I'm going to swing back here real quick just to write the word on the board. A-S-Y-M-P-T-O-T-E. Asymptote. It's easy to skip the P and just say asymptote. Plural is asymptotes. But in the next video, or maybe a couple down the road, we'll formally define what an asymptote is. But for now, all it is, see there's the table I'll put the camera on. All it is a line that's not really part of the graph, but it kind of serves as a boundary. For example, let's look over here out to the right. And we'll zoom in the other way. Let's go over out there some. All right. So you'll see this graph right here is getting real close to that red line. And at this point, it has the illusion that it is actually, the graph is actually on the red line. But if we were to zoom in, and I'm going to put this in the center so that I can, no, that's not what I meant to do. I'm going to try to put this in the center. Stop it. I'm going to try to drag the graph here, put this in the center and zoom in on it so that it stays centered there. But as we get closer and closer, you'll notice that, well, there's something I wasn't expecting. The graph is actually above the red line, but it's not on it. Let me zoom out. I didn't think it crossed, but it must, because here it's below and then it's above. But if we were to keep going further and further out, even further than this, let's do what I call a Google jump. A Google jump is where I zoom out really, excuse me, not zoom in, zoom out really far, and then I drag the graph over some, and then I start zooming in. I call it a Google jump because if you've ever used Google Earth and gone from one point on the planet to another, it looks like you jump up in the sky. And that's what it kind of reminds me of. Zooming out looks like we're jumping up in the sky. And then zooming in means we're crashing to the ground. Uh-oh, lost it, come back down here. Anyway, if we go out really far, it looks like the graph is on that dotted line, but if we zoom in enough, you'll start to see that that's not actually the case. So almost there. You can start seeing a gap form between them. Yeah, that's good enough. So even though way out on the graph, it looks like the graph and the dotted line coincide, there's actually a gap between. It's just that the gap between them is smaller than the pixel size on the screen, so you can't tell the difference. Let's go back to the default zoom. All right, so I want to describe what's going on here. And in the next video, I'll go to the board and show you how to denote this. We're going to see a new symbol. In fact, I'll show it to you now. A new symbol. Actually, I've shown you this symbol before, but in this context, it has a different meaning. In symbolic logic, this symbol means implies. If something happens, that implies something else happens. But in calculus, this is the symbol for the word approaches. Excuse me. And what it means for a variable to approach another one is to get closer without actually ever reaching it. For example, let's say you take the number 1 and you cut it in half. If you cut it in half, you get a half. And if you cut it in half, you get a fourth. And if you cut that in half, you get an eighth. And if you cut that in half, you get a 16th. These values are approaching something. They're approaching 0. They'll never get there, because if you take half of something, you still have something. But if you keep taking half, it gets smaller and smaller. What it means to approach is to get closer and closer without ever reaching it. In other words, you can get as close as you want without touching it. So in this case, if I keep cutting in half, I can get as close to 0 as I want without ever getting there. So what does that mean over here? Well, there's two versions of this approaching thing. Number 1, what happens is we approach a vertical line. For example, let's say I get on the graph right here. Actually, let me fiddle with this slider. 1 second, folks. Okay, so let's drag this back towards the middle of the graph, right about there. Here it comes, there it goes. Okay, slow down, slow down. All right, I'm gonna animate this. Hopefully it'll go the direction I want. Yes. Okay, so here's what I want you to watch. As this point starts getting closer to this red line, I want you to watch at its y coordinates, its second coordinates. And I'm going to try to stop it before it shoots off into the sky. So, okay, here they go. All right, 0.2, 0.3, 0.4, 0.4. Whoa, 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 whoa. I couldn't even call the numbers, they were going up so fast. So let's animate it a little bit more and hopefully it won't go past 1.81. Whoa, whoa, it went past, hold on. It's almost like it warped to the other side. Let me see if I can slow this down. No, it's actually going as slow as it's going to go. Let's do this, let's zoom in on it. Okay, and let me see what happens if I animate. Oh, I know what I can do to slow it down. I thought I had this set the way I wanted before, but I'm making one more adjustment. Okay, here we go. Okay, it's not going as, well. Okay, so we'll forget about the fact that I can't make it move as slow as I want, and we'll just drag it over here. As I move this point, as it gets closer to the line x equals 2, what's happening to the y value? It's going to skyrocket. In fact, the way this red line works is the closer I get to this red line, the bigger the y value gets. So as we get closer to a vertical line, a vertical asymptote, we can expect the graph to explode either up or down. If you notice on this side over here, as I approach from the right side, it's going to plummet down to downward forever towards negative infinity. Now there's another type of approaching is if you let your x's get really big. Like if I let this x go forever to the right, what's happening to the y values? Well, the y values look like they're getting closer to -1. Let me hop on the graph here. Here it is. The y values, it looks like they're going up, but at some point they're going to start going down and getting closer to -1. So in the next video, I'm going to show you exactly how to describe these phenomena. The phenomenon of when you get closer to a vertical asymptote, the y values are getting ridiculously large, and when you get closer to a horizontal asymptote, the y values start settling down.